The major functions of any compressor case, regardless of type, are to provide support of all bearings, seals and stationary internals, provide positive containment of the process fluid, and provide efficient guidance of the process fluid. Let's start with the first function. Often, the support function of the casing is not mentioned when stating the major casing functions. Excessive casing forces caused by the process piping or foundation can cause bearing, seal, and rotor failures. Positive containment of the process fluid is accomplished by the design and manufacture of leak-tight joints. All casings are hydrostatically tested at 1.5 times the maximum working pressure prior to the shipment. Gases containing more than 50% hydrogen require a gas test at rated pressure in addition to the hydrostatic test. Casing joints are either horizontal or vertical. Horizontal joints are usually metal to metal as opposed to vertical joints which always incorporate an O-ring. Some manufacturers do incorporate an O-ring in their horizontal design. But in my professional experience, metal-to-metal horizontal joints are preferred to make sure that a leak will not develop if the O-ring is damaged. Now, barrel or radially split casings, as seen here, are used for gases with high hydrogen content or for pressures above 600 psi. The advantages of the barrel-type compressor are minimum casing joint area and removal of internals with removal of process piping. The disadvantages for this type of compressor casing are special tools are required for the disassembly, and additional maintenance space is required for removal of internals. So, if you have a two-case application using barrel-type compressors, I strongly advise you to design the driver with double shaft extensions to facilitate the task for the maintenance team. The available types of compressor casings are single-stage radial split, single-stage integral gear, multi-stage radial split, multi-stage horizontal split, and multi-stage integral gear, as depicted here. The figure that you can see here is an example of a single-stage radial split casing. This type of casing is typically used for high-pressure applications and for gases with high hydrogen content. Its design is similar to that of a single-stage overhung centrifugal pump. The design shown here is back pull-out. That is, the impeller must be removed for seal or shaft removal. Other designs allow front pull-out. This type offers the advantage of removing the internals of the compressor without having to remove the process piping. Let's have a closer look. So here you have the section of the compressor and here the discharge. Here you can see the impeller, the eye of the impeller, the rotating shaft, the journal bearings, the thrust bearing, and the mechanical seal. Now, in order to extract the impeller or the shaft or the bearings, you have to do it in a back pull-out way. In other words, the impeller, the rotating shaft, the mechanical seal, the journal bearings, and the thrust bearings must be dismantled in this direction, which offers an interesting advantage since you don't have to remove the compressor process piping and connection. Let me now show you a real example of one of our back pull-out single-stage radial split compressors used in our petrochemical plant. So if you remove the rotor and the bearings and the seals, which is the piece highlighted here in yellow, if you remove or extract this piece from the backside without removing the process piping, then the piece you will extract will look like this, with the impeller on the right side and the shaft and the bearing and the mechanical seal on the left side. An example of a multi-stage radially split or barrel compressor is shown here. Here you can see the casing of the compressor, the rotating shaft, the impellers, the balance drum, the journal bearings, the thrust bearing, and the mechanical seals. We will now proceed by dismantling this compressor step by step until the casing is the only piece remaining. To do that, first we begin by removing the bearing housing cover, as seen here. Next, we split the thrust bearing assembly. Then we remove the thrust collar. Then the coupling. And then we remove the journal bearings on the non-drive side. Then the drive side. Next, we remove the mechanical seals on both shaft ends. Then we unbolt the casing to remove the cover. Now we can extract the rotor. And there you go. This is the casing of a barrel compressor with its cover without any internals. This next figure depicts a multi-stage horizontally split centrifugal compressor. Here you can see the casing upper half, the casing lower half, and the bearing housings. Let's apply the same methodology and disassemble this compressor step by step until the casing is the only part left. We begin by inbolting the casing and removing the upper half of it. On removing the casing upper half, you can see that a diffuser assembly exists below the casing. So let's remove the diffuser upper section. Now we can see the rotor or the shaft and the impeller assembly. Let's go further ahead and remove the rotor to examine the casing lower section. And here you can see the casing and the diffuser lower sections from a different angle. You can see here another example of a multi-stage horizontally split centrifugal compressor. Most multi-stage compressors used in the industry and the ones I have come across are horizontally split and should be used whenever process pressures and gas compositions permit. The advantage of a horizontally split casing should be ease of removal of internal parts. The example that you can see here meets this requirement, since all process piping is located on the lower half of the casing. When process piping is connected to the top half of the compressor casing, as seen in this example, the maintenance advantage is lost. So my advice to you, get yourself involved in the initial process plant design to make sure bottom connected horizontal compressor cases are installed. And so have a cost analysis performed to determine the additional cost for bottom connections. And when performing your cost analysis, be sure to include the cost penalty for the additional removal and assembly time for top-mounted piping. Also, be sure to include the revenue lost per day of additional downtime if the compressor is unspared. Just for your information, typical additional times for piping removal and assembly are around 2 to 3 days and sometime longer. So if the cost is prohibitive, another option would be a barrel compressor with top connections, as depicted in this example. Various casing fabrication options exist. Casings can be cast, forged, or welded. Older designs were generally cast. However, foundry quality has decreased, and today many casings are welded from steel plate. Compressor vendors have existing qualified procedures and welders to fabricate these casings. The figure that you can see here is an example of a cast casing, and the one that you can see here shows a fabricated barrel compressor casing. In high pressure or high hydrogen gas applications, forged barrel compressors are required. In this design, the entire barrel casing is on continuous forging, as highlighted here. However, cast nozzles are welded onto the casing. The common approach used today in the industry is to accept either a fabricated or cast casing, as long as the compressor vendor has proven experience with the offered design. However, regardless of the type, keep in mind that all hydrocarbon services, in particular those found in petroleum refining or petrochemical, all of them require steel casings. As discussed in a previous video, casing stresses and deflections caused by excessive piping or foundation forces can cause damage to bearings, mechanical seals, and other internal components of your compressor. There are standard checks during compressor field construction and disassembly to make sure that the values of all external forces and moments on compressor cases are within prescribed vendor limits. During the compressor design phase, the vendor issues an allowable piping forces and moments diagram, which states the maximum values of external forces and moments to which the casing can be subjected. The piping systems are then designed to comply with these limits. However, elements such as field piping fabrication methods, field foundation building, improper spring support sizing can result in excessive case stresses even though the systems were properly designed. Therefore, field checks of proper piping connections and foundation fabrication are required. The basic philosophy of these checks is to make sure that the casing is not deflected. This is done by checking the movement of the rotor relative to a fixed external point and the movement of the compressor base plate relative to a fixed external point. Prior to conducting field checks, it is advisable to make an inspection of external piping system condition. And here are some useful guidelines for this inspection. First, float process piping to compressor connections and confirm bolting is free without use of come-alongs, and that machined faces of flanges are parallel within the tolerance indicated here. If these conditions are not met, then take corrective action before proceeding with the field checks. Possible corrective actions can be loosening piping flange connections away from the compressor to meet requirements, then retighten while performing field check, or correction of spring support or spring hanger sizing and installation, or heating piping to meet requirements, or finally cutting and re-welding piping. The field check to make sure that the foundation is not exerting excessive force on the base plate is known as the soft foot check. The guidelines are shown here. The field check guidelines to make sure that the process piping is not exerting excessive forces on the compressor are shown here. These guidelines are available as a PDF downloadable file at the end of this section. So I strongly encourage you to take a look at them, examine the steps carefully, and feel free to ask us for help or more details in the Q&A section. Just keep in mind that excessive casing forces from process piping and foundations are one of the major sources of misalignment. So my advice to you, talk with your maintenance team and stay informed and updated of any work on process piping systems or foundation, and prepare guidelines to control and monitor this work.